notebooks. Go ahead and grab your lecture notebooks so you can be filling in some blanks here. Got a little bit of this going on. All right. So we're going to build on what we've been talking about with regard to molarity. And we're going to do some kind of dilution problems. The way dilution problems go is, for me, they definitely need a picture. So a lot of times if you stop by for help with a dilution problem, solution concentration, dilution problem, I will draw a picture. And usually it goes from left to right for me. So in dilution problems, you usually have a stock solution. So here's my stock solution. Here's my volumetric flask. It's kind of an ugly volumetric flask. And here's another volumetric flask. I'm just kind of showing you how we make diluted solution. This is called your stock solution, SOL''N, and this is your diluted solution. And as you can imagine, you know, M of course stands for molarity. Molarity is going to be in there somewhere. But basically you transfer a certain amount of your stock solution into a waiting volumetric flask. So you transfer stock solution. And then you'll have a little bit of residue down here, and then you'll go ahead and add water. Remember how volumetric flasks work, is there's a line up here, you add water up to the line. So that's kind of the process of preparing a diluted solution. Now, a reason why you might want to, if you had, how do I say this? If you have a very dilute solution you want exactly perfect, it's easier to make a concentrated, so this is concentrated. It's easier to make a concentrated solution first, just right on the nose, and then to transfer a certain amount of that over. Okay, that's just, it's I say easier, it's more accurate. Notice, like it says in italics, over here, your just diluted solution will have a lower concentration than the original. So let's work a few problems, and I'll just kind of go ahead and work with what I got up here. I'm going to pull those numbers out and put them on my drawing, my kind of ugly looking drawing, but I know what it's supposed to be. So it says that 25.0 milliliters of a 0.160 molar calcium chloride solution is pipetted into blah, blah, blah. So kind of from left to right, that first volume, the molarity, has to do with my stock solution. So over here, I'm going to write 0.160 molar CaCl2. We've been talking about unpacking in here. What that really means is 0.160 moles of the solute, CaCl2, per 1 liter of this solution. That's one of the reasons I like pictures, because I'm like, oh, well, that's all associated with my stock. Because you're going to see when we work these problems, you're going to have kind of different things going on with your stock and your diluted solution. So my transfer aliquot, we've used that word before, I like it. An aliquot is just simply a small piece of a liquid. So my transfer aliquot is 25.0 milliliters. I'm going to go over here. I see that the capacity of this vol flask is 125. We're going to go with 4 sig figs milliliters. So I'm going to transfer that cute little aliquot over, put it in here, and then dilute it up with water. The question is, what is the molarity of my diluted solution? So there's different ways to work this, and I'm just going to kind of tell you what you're going to see in the next few slides is I am going to, step number 1, I'm going to come up with moles of CaCl2 transferred. That's step number 1. And then I think I only need another step. So that was the moles of CaCl2 transferred, and then I'm going to divide it by this volume. So step number 2, I'm just going to take moles of CaCl2 divided by new volume. I'll put DIL for diluted volume. That's it. That's totally it. So here we go. So we know how to get moles from volume, 25.0 milliliters, and molarity, which is 0.16 molar. Problem is, well, it's not much of a problem, is we've got milliliters here. That's our aliquot volume, and our molarity is in moles per liter. So we're going to have to fix our milliliters. How do I go from milliliters to liters? Yep. 1 liter over 1,000 milliliters. Perfect. And now I'm going to use molarity. Am I going to use it just like this, or am I going to flip it? How many people think it's just like this to get to moles? How many people think I'm going to flip it? Oh, we're kind of split. So I have liters here. So how many people think I'm going to use it just like this? Oh, we're getting a little more heavy on that side. So I'm going to use it just like this. Yep. If I go ahead and insert that now liter of solution cancel, and I have units of moles, which is what I was after. And actually, that's the end of that first little step. So I'll kind of be jotting this down in your notebook. Yeah. So how many sig figs? I'm liking 3. Yep. So to give it 3 sig figs is kind of a weird number. So 0.00400. And then units, of course, would be moles of CaCl2. And again, I said this before, but see how I actually kind of labeled what I was doing. And in chemistry, there are certain problems where it's nice in the blue up there, if I label what I'm doing. So now I have the moles of CaCl2 transferred. What did I tell you step number 2 is?
To divide it.
Yep, just to divide it. And I'm going to have to fix my units of volume. So here we go. I just divided. So all of those moles in that 25.0 milliliter aliquot ended up in my 125.0 milliliters ball flask. So now how, this will give me moles per milliliter. How do I get moles per liter? Times 1,000. Yep, 1,000 milliliters over 1 liter. Yep. And how many sig figs? Let me think. I'm liking 3. Yep, there's 3 here. These aren't significant. And there's 4 here, but we'll always go with the fewer. Yep. So 3 sig figs. You're probably, like I told you before, I get tired of writing explicitly. You're probably going to see me go 0.0320. That gives me 3 sig figs. Big M for molarity, that's what I was after. And my solute is CaCl2. The ratio up there is writing it explicitly. So this was not significant. 1, 2, 3. Yep. That's it.
Is that the canvas cup?
Is that what?
A canvas cup?
It is a canvas cup, yep. I presented one time and they said, here, take this cup. I don't have my other bottle, so. I have a little video to kind of show you. Of course, we've been talking to dilute up and all that, and you guys have been using a pipette, and pipettes come in different volumes. The ones you guys have used has been 10.00 milliliter. They have a 2.00 milliliter. We've got a 50.00 milliliter. So let's work another problem. Let's just kind of erase a few things, and I'll use my same volumetric flasks. But notice one of the things we run into in chemistry problems is there's so many different kind of variations, and let's kind of see what this variation is. We're not going to get to all variations, but okay, so it talks about the stock solution. It gives me a volume, and I see that my solute is potassium dichromate. So here, transferring, I'm going to put 2.00 milliliters of an aliquot is transferred. Okay, over here, we've got this volume that I'm going to dilute it up to is a 500 milliliter vol flask. All right, so this is a little different. Notice I'm not given the molarity of my stock, but I am given the molarity of my diluted solution. So over here on the right, I'm going to put 1.60 times 10 to the negative 4th molar, and the solute is K2Cr2O7. So what that means, I'll go ahead and unpack that. It means for my diluted solution, I have 1.60 times 10 to the negative 4th moles of K2CR2O7 potassium dichromate per 1 liter solution. Now, granted, I have 2 solutions, but since I'm writing it over here on the right, I know that that's my diluted solution. And so the question mark is, what is the molar concentration of my stock? We can do that. When we work a problem like this, sometimes I say, what do you know most about? In this case, diluted or stock. To me, what I know most about is the diluted solution. Do you see where step number 1 here is going to be simply to we can take the volume and the molarity to get moles. So step number 1 is moles of K2CR2O7 floating around in there. Step number 1. Moles of K2CR2O7 in diluted solution. Then once I get moles, it's like reverse engineering kind of. Those moles all came from this cute little aliquot. So the last step, 2, is simply to take those moles and divide it by my transfer volume. I'll put moles of K2CR2O7 divided by 2.00 milliliters. Okay, then we're done. That will give me the molarity that aliquot must have been. So here we go. Again, it's kind of, I feel like reverse engineering. So I'm going to put my 500 milliliters over 1 with 4 sig figs. And so now how do I get 2 liters? Times, I want milliliters to cancel though, so.
Times 1 over 1,000.
Yep, 1,000 milliliters in the bottom, 1 liter in the top, perfect. So now how can I use this molarity, because we're talking about the diluted solution. How many people think I'm going to flip that? How many people think I'm going to leave that the way it is? Yep, I'm just going to plug that number in. Very good. So my next term is the molarity of the diluted solution, and that's 1.60 times 10 to the negative 4th moles of K2CR2O7 per 1 liter of solution. Now, granted, like I said a minute ago, like Mrs. Snipes, you have 2 solutions. You didn't say which solution, but I said it in my picture. I'm talking about the diluted solution. So how many sig figs? 3, exactly. Because there are actually 4 sig figs here. There would be 4 here. And there's no uncertainty here. And there's only 3 sig figs here. So, yep. So I get, and I still left it packed up in scientific notation because it's got some of those leading zeros. 8.00 times 10 to the negative 5th moles of K2CR2O7. I just think that's kind of fun to think of them all swimming around and playing in my diluted solution, but they came from that 2 milliliter aliquot. So now how can I get molarity? Yep, take that divided by the aliquot volume. That's it. Sometimes, and we didn't use the molar masses, did we? I was going to say, when in doubt, use a molar mass. We have not used a molar mass. A lot of times we don't in this type of kind of back and forth between volume and molarity. No molar masses. When I start to say sometimes don't make it more complicated than it should be. So I need a term to get units of liters in the denominator. What does that look like? 1,000. Yep, 1,000 milliliters solution over 1 liter of solution. Perfect. 3 sig figs. And this is what I get. So notice to show 3 sig figs, I need 2 trailing zeros after the decimal. Okay, so many variations. So. And sometimes, I don't think I'm necessarily going to cover them in this class, but there's what's called a serial dilution. So if you need a really precise, really diluted solution, what you would do is to continue this process. Like I might have another vol flask and another vol flask here on the right. And I would take an aliquot of this and dilute it up. And I would take an aliquot of this and dilute it up. Okay, so serial dilutions, and you just keep track of what your molarity is as you go. So this is a heads up that our textbook, OpenStax, actually uses the C1V1 is equal to C2V2, and I understand the concept very, very clearly, but you cannot use this for Gen Chem 1. If you stay in Gen Chem 2, you can use it in Gen Chem 2. Just to let you know what C1 and V1 and C2 and V2 are, basically, if you replace the subscripts 1s with stock solution and the subscripts 2s with your diluted solution, that's how it works. So, for instance, in this case, our question mark would be C for concentration, question mark concentration 1. We could rearrange this and say the concentration of our stock, molarity of our stock, will be equal to the concentration of our diluted times the volume of our diluted divided by the volume of our stock. I just throw that out there. Okay, so these are due Thursday. I double checked. I think there might be 2 parts, but
Yeah, you put it part A, part B.
okay, thanks. So we're on to part 12. Smiley face. And it looks like this. And it will definitely feel familiar in a way. But what this does is it brings in what we've been talking about, molarity and volume and moles, to what we know about a balanced equation. A balanced equation gives us the stoichiometry of the reaction. So, oh yeah, I printed this out. So I thought this is quite clever. So everybody gets a copy of the stuff we've been working on already. Okay. Oh, sorry. They'll show up when you're not looking for it. Least expected. So, I mean, if we look at, like I said, it's stuff we've been doing. So, for instance, moles to moles, we know that we use a stoichiometric ratio, right? Most recently, we've been using molarity to go back and forth between volume and moles. So the way you read this is the boxes are what you want to get to or what you know. And then over that, the arrow actually tells you how to make that happen. Okay? So right now what we're going to do is we're going to kind of go focus on this right here. We're going to be talking about two reactants, or a reactant or product, or 2 products, A and B, and we're going to be able to go back and forth between volume of one solution to volume of another solution. And you recognize, again, I said stuff we've been doing. You guys know to go back and forth between number of particles and moles, you're going to use Avogadro's number, whether that's solution A or solution B. Okay. So, aqueous solution stoichiometry. Ugh. It's all wonderful though. Aqueous solution, we know, solute dissolved in water. We're going to use what we know about how it's concentrated with regard to molarity. And we're going to tie that, like I said, into the stoichiometry of a reaction that's going to happen in your aqueous solution. Okay. So, very common things are to knock out the concentration of a solution and or knock out the volume of solution. You need to go ahead and reach what we call the stoichiometric endpoint, and I'll kind of be talking about what that looks like. So if you have a relationship, in this case molarity we know is a ratio of moles to volume. You know how this works is if you know any of those 2 quantities, you can get to the third. Okay, it's math. So here we go. Let's work this problem. I'm not going to draw a picture, but what you've seen me do with stoichiometric calculations is I'm actually going to write quantities underneath the species in the balanced equation. So here we have sulfuric acid reacting with sodium hydroxide to form sodium chloride and water. Or, excuse me, not sodium chloride, sodium sulfate and water. And here's the question. And again, there's so many different, slightly different variations of this that you could run into. So it says, what volume of 0.235 molar NaOH? So I find my NaOH and I write question mark volume, question mark V. Okay. Also under the NaOH, I get all excited and I write 0.235 m for molar. Okay. Then I continue reading, and it says is needed to react with 35 of 0.108 molar H2SO4. So I find my H2SO4 and I write 35.0 milliliters and I write 0.108 molar. Well, a little bit ago, when we were doing a problem up here, I said, what do you know most about? And I'm going to ask you guys for this. What do you know most about? Your options are H2SO4 or NaOH. How many? Yes, we know more about H2SO4. Perfect. So actually what you're going to see on the next slides, I can write step number 1. Do you see where we can get to, we're going to calculate the moles of H2SO4. Can you kind of picture that? I bet you're okay with that. And this is using volume and molarity. Step number 2 is to go calculate the moles of NaOH. How are we going to get from moles of NaOH, and actually it's on the sheet I gave you, to moles of H2SO4 to moles of NaOH? How are we going to do that? What does it say right in the middle?
Stoichiometric.
Yep, stoichiometric ratio, exactly. Stoich. Okay. Then, once we have the moles of NaOH, can you see where we're trying to get to the volume? We can get to the volume now because we'll know from moles and molarity. I don't know how to say that. I'll say we will have moles from step 2, and we're given molarity. Big M given. So anyway, we're done. And that will take us to volume. Okay, so here we go. And if you label what you're doing, like on my slides right now, the blue is the label. If you label, then you don't have to be explicit about what species you're working with. So you guys told me I know more about the H2SO4, so I'm going to focus on the H2SO4. I am going to moles of H2SO4 here from volume. How do I get from milliliters to liters?
1 liter.
Yep, 1 liter or 1,000 milliliters. Perfect. And now I didn't unpack it for you guys yet, but you guys know how this works. That big M, 0.108 big M means 0.108 moles of H2SO4 per 1 liter of solution. So how can I use a ratio now here to get liters of solutions to cancel and be left with moles? Do I leave it or do I flip it? Yeah. It's kind of hard to answer that question, but yeah. Yeah. I would call it the non-flipped version of the molarity. Because just the number 0.108 big M means 0.108 moles in this case of H2SO4 per 1 liter of solution. Yep, so now milliliters cancel, liters cancel, we're left with moles of H2SO4, which actually that is our step 1. So we have arrived. You probably tell me 3 significant figures. So I get 0.00378 moles of H2SO4. Now, I don't think I've run into a lot of this on your test, but you want to really avoid what I call run-on equalities. You need to present your work as clearly as possible for you and for my sake. So I'm gonna actually, for my next step, I'm gonna rewrite this number. I'm not just gonna continue on. So if I rewrite this number, it looks like this, 0.00378 moles of H2SO4. We said now I'm gonna use a stoichiometric ratio. And I want moles of H2SO4 to cancel. I'll kind of point out the balanced equation down here. I want moles of H2SO4 to cancel, and I want to be left with moles of NaOH. So what does that ratio look like?
2/1.
I heard 2/1, and I'm sure you would write units with that. So
Yes.
yes. So exactly 2 moles of NaOH over 1 mole of H2SO4. Perfect. I'm totally digging that. So the 2 and the 1 bring no uncertainty, so you're still looking at 3 sig figs. So that means the moles of NaOH I get are 0.00756 moles of NaOH. So that's step 2 of 3. And step 3 then was to use what we now know, the moles of NaOH, and we were also in this case given the molarity of NaOH to get to volume. So I'm going to rewrite that number on my last step. So 0.00756 moles of NaOH. So the molarity was given. How can we use the molarity to our benefit to have moles cancel, be left with liters on top?
So you put 1 liter over, what was it?
I have to look back too.
1, 2, 3.
Yeah, exactly. She's looking back. Exactly. In the original problem, it was 0.235 molar. So this is what I call the flipped version of molarity. So I put 1 liter of solution on top and 0.235 moles of NaOH at bottom. Moles of NaOH cancel. Now this is where, and I can't remember what my fields do, but did it say liters or milliliters? I don't think it said. Sometimes,
what volume?
yeah, if it asks for just what volume, you can leave it at liters. Sometimes I will ask for how many milliliters, and I can't remember today. Oh, it looks like I'm going for milliliters. So you wouldn't have to use this last term if I asked this on the test. But milliliters are kind of easier to sink your teeth into, usually with solution volumes. So I'm going from liters to milliliters this way. So 3 sig figs then will give you, and then the units will be, in this case, milliliters. So 32.2 milliliters of solution, specifically NaOH solution, as kind of indicated by my blue title. And that's it. Again, and I think maybe that's why I kind of pass this out. I kind of make a big deal. Oh, when in doubt, use the molar mass. We did not use the molar mass, did we? So we just did this one right here. But I will warn you that sometimes, if you're kind of following how this works, sometimes we're doing a solution stoichiometric calculation where one of the reactants is a solid and one is a liquid. And then you kind of have to go this way to kind of do your calculation. And just for kicks, let's look at what we've been doing. Oh, wait a minute. No, that isn't what I meant. Right here. Yeah. What we've been doing, like right here, we've been doing this one right here. Ordinary stoichiometric calculation. Right here. We've been doing. This is a stoichiometric calculation. Today we're doing this one. Yeah. Okay, let's do one more, and this will set us in good shape for tomorrow. So, same reaction. Let's look at what we got though. It says, I'll find my H2SO4. It says, what is the concentration? So for H2SO4, I'm going to put question mark molarity. You might be like, well, Mrs. Snipes, how would I know concentration means molarity? You just do. What is the concentration molarity of H2SO4? And then it gives me if 20, I have to read it a few times sometimes, 25.0 milliliters of the solution. So to me, that's talking about my H2SO4 solution. So under my H2SO4, I'm going to put 25.0 milliliters of the solution required. Now I've got a volume and a molarity and the word NaOH after it. So actually, my 27.7 milliliters goes with my NaOH, 27.7 milliliters. And then the other thing that goes with my NaOH is the 0.444 molar. So now what do I know more about? Yep, now I know more about the NaOH. It's going to feel very similar. My first step is going to be moles of NaOH. And I'm not going to write down how we do it, but because I think you guys are all on board, we're going to use this volume and this molarity. Once I have moles of NaOH, the second step is going to be the same what we did before. I'm going to get to moles of, in this case, H2SO4 using stoichiometric ratio. Stoichiometry. Stoich. And then the last step, once I have moles of H2SO4, I can just take those moles and divide it by that volume to get molarity. Step number 3 is moles divided by volume. Moles H2SO4 divided by volume. I'll put V for volume, and that will give us molarity. So the first 2 steps seems like they have a very similar approach, similar thing we do. The third step will change up a little bit in this sort of problem. All right, so here we go. The first step is to use the volume and the molarity of the NaOH to get to moles. So I need to take those milliliters and get them into liters. How do I do that? 1 liter over 1,000 milliliters. So my units of milliliters will cancel. Perfect. Now I'm going to use molarity to get to, molarity means in this case 0.444 moles NaOH per 1 liter of solution. So do I use it like that or do I flip it? Use it like that, yep. Because the way I unpack it, liters are already in the denominator and I want them to cancel. Yep. Okay, so cancel. I love canceling things. We have moles of NaOH. So 3 sig figs, you're looking at 0.0123 moles of NaOH. So again, don't do a run-on thing. Rewrite that number for your second step. So I would rewrite that number then. I'm going to put 0.0123 moles of NaOH over 1. Here's so here's the balanced equation down here. I want moles of NaOH to cancel. I want to be left with moles of H2SO4. How does that look?
1 H2SO4 over 2.
Yep. 1 mole of H2SO4 over 2 moles of NaOH. Perfect. I'm still allowed 3 sig figs, and that simple calculation will give me moles of H2SO4. So you're looking at 0.00615 moles of H2SO4. So this is the second of 3 steps. So what did we say would be the third step?
Moles divided by volume.
Moles divided by volume. That's it. So again, I'm going to start a new line. I'm going to take that number. So just to reiterate, if I see a bunch of run-on, hard for me to follow, like to use the word crap, on your test, working a problem like this, and you will see a problem like this on your test in some form, I will get frustrated, even if you get the right answer. I'm going to rewrite that number. I'm going to put it over the volume, which was 25.0 milliliters, but that won't give me molarity. How do I need to fix that?
Times it by 1 liter. Wait, by the 1,000 over.
Yep, you're both right. Times it times 1,000 milliliters over 1 liter. Perfect. So I'll give myself 3 sig figs and a pat on the back. Okay. So you're gonna see me write down 0.246 big M and my solute H2SO4.
So how do we know, like, that we needed to do the mole divided by 1? Like, how do you tell from this?
Well, I don't think you can necessarily tell from this, but I would tell it by, in my heart, what I know the definition of molarity is. So molarity is moles divided by volume, and that was what that was my question. Yeah, just kind of by definition. Yeah, I couldn't necessarily use this. Okay. So when we come in Wednesday, we'll pick up here, and this should work pretty good, I think. Knock on wood. So, see, I know it's not wood. We'll see you on Wednesday.